Welcome back. We're going to do another example of gas stoichiometry. So this reaction takes place in a lab. This is actually something that you've probably done before. It's a very easy experiment to show to high school students. Take some magnesium ribbon, some metal, and you put it in a test tube of hydrochloric acid. And it's kind of fun. You can hold your thumb over the test tube, collect a little bit of hydrogen gas, which is one of the products. And then you can bring a splint nearby, open up the test tube, and you can blow up whatever hydrogen gas you collected. And usually you only collect enough that it gives you this nice little pop sound. Anyway, things I wish we could be doing right now instead of being in COVID-19 lockdown. All right, so let's start off by writing out the balanced chemical equation. So what is actually going on? Let's read this again. What volume of hydrogen gas is likely to be produced from the reaction of magnesium metal with sufficient hydrochloric acid? So I've got magnesium plus hydrochloric acid. Once again, pause the video and think through what the other product is likely going to be. One of them's hydrogen gas. What would the other one be? And have a look too at the what type of reaction is probably going to be. That might help you predict what the products are going to be. All right. So this is a single displacement reaction. So the magnesium is going to kick out the hydrogen and form magnesium chloride. And the other product is hydrogen gas. And to balance this, I need to put a 2 in front of the hydrochloric acid. And looks like we're ready to go. So it says that we start with 33 milligrams of magnesium metal. So 33 milligrams. And to convert, 1,000 milligrams makes up 1 gram. So just need to divide this by 1,000. So 33 divided by 1,000, and that'll give you your mass in grams. So that's going to be 0.033 grams. Okay, next thing I'm going to do is I'm going to convert this to moles of magnesium. So the molar mass of magnesium metal is just 24.31 grams per mole. My number of moles of magnesium will be 0.033 grams times the conversion factor. And in my conversion factor, which is my molar mass, I need to put the mass on the bottom. So in effect, this is like dividing by the molar mass, or at least the number that represents the molar mass. So, all right, so this is going to give me some number. I'll just record it here, but once again, I can't say this enough. Do not round till you get to your final answer. Okay, so that's a pretty small number. That's 1.4 times 10 to the negative 3 moles of magnesium. Okay. Now it says we have sufficient hydrochloric acid. We don't need to worry about hydrochloric acid yet. We are now needing to convert these moles of magnesium into a volume of hydrogen gas. So let's make our mole ratio. What's the mole ratio between magnesium and hydrogen gas? Well, it looks like it's a 1-to-1 ratio. So that means 1 mole of magnesium consumed will produce 1 mole of hydrogen gas. So that means my number of moles of magnesium equals my number of moles of hydrogen gas. Great. So what else do I know about the hydrogen gas? Well, I know I know it's number of moles, so let's give that a check. What else do I know from the write-up? I also know it's pressure. Pressure is 93 kilopascals, and I have a temperature which is 23 degrees Celsius. Convert that to Kelvin. So it's 23 plus 273.15. I get 296.15 Kelvin. So I've got number of moles of hydrogen, I have its pressure, I have the temperature. There's that last check mark over there. I didn't forget about temperature. And so I've got moles, pressure, temperature. What could I use to convert all of these into a volume of hydrogen? Well, I could use the ideal gas law. So I can take these and plug them into the ideal gas law. So volume equals moles times the ideal gas constant times temperature over pressure. And this is just a rearranging of the ideal gas equation. All right, so I can plug all these numbers in. So I'm not actually going to write down every single number here. Oh, that should be an R. So the ideal gas constant, in case you forget, it's 8.31. Units are liters, kilopascals, moles times Kelvin. All right, let's put all this stuff in. So number of moles of magnesium were 0.033 over 24.31. So there's my moles of magnesium, and then we said it's a 1-to-1 ratio, so my moles of magnesium equals my moles of hydrogen, which I'm going to use in that equation. So I'm just going to take that number and I'm going to multiply it by 8.31. I'm going to multiply it by my temperature. And then I divide by pressure, which is 93.0. Okay, and I get an answer of 0.0359. Here's where I need to consider my significant digits. And looks like I'm going to have 2 significant digits from my mass. So I'm going to write it out as 0.036. The 9 rounds the 5 up to a 6, like that. Okay, so that's 0.036 liters, or you could also say 36 millimeters. Either one's fine. All right, so there's some gas stoichiometry for you. Not all that different. Once again, the key ingredient is the mole ratio. We convert everything to moles. We use a mole ratio. The only things that really change are what we do after that, or what we do before it. You know, we might start with a mass, or we might start with concentration or volume in case we're working with solutions, or we might have a gas as a reactant, and we might have to use the ideal gas law or some other law to convert to moles. But we're always going to funnel and reduce everything down to a mole ratio, and then we're going to work our way back up again to whatever we're being asked for. In this case, we're being asked for a volume of hydrogen, so 36 mils. All right, so that's that for this video. See you in the next one.